everybody, Mr. Cope here. In this video I am going to be showing you guys a little bit about potential and kinetic energy so that you are able to understand how these two types of energy work, what they are, and how to do some calculations with them. So let's get going. So how is all energy divided? So energy usually is broken into total mechanical energy, which is then broken down into potential energy and kinetic energy. Kinetic energy is very straightforward, whereas potential energy could also be one of three types of potential energies. There's gravitation potential energy, elastic potential energy, and chemical potential energy. Now, when it comes to total mechanical energy, we think about conservation of energy. Energy cannot be created nor destroyed. So in a system, the total mechanical energy is always going to be the same. The big difference is, and how energy changes, is just changing what type of energy. But overall, energy will always stay the same in a system. And this is really important because when we're doing, or when we're looking at our kinetic and potential energy, the sum of these two energies will always still be the same. The difference is which one has a greater amount. So is there a lot of potential energy and a little kinetic energy, or a lot of kinetic energy and a little potential energy? With that, let's look at potential energy first. So potential energy is just energy that we consider to be stored. It's waiting to be used. So you can think of like these two examples here. This kid is playing with a bouncy ball on an elastic string, and as he bounces it away, the string stretches out, but then it pulls itself back. And that is the energy, that's the potential energy that pulls it back in as it's building up. So you can think of, if you're maybe doing like a rubber band, when you pull the red rubber band, you stretch it out. It's not moving once you're fully stretched, but there's a lot of energy there that's potential. And if you just let it go, it's going to shoot out of your hand. The other one here, typically when we think of potential energy, we usually think of things at a height. So like in this example, we have this height that weight is going to drop. And when we cut the string, the potential energy is going to convert to move it. So elastic potential energy is the first one I'm going to look at. And elastic potential energy is just energy that comes from the compression or the expansion. So you can imagine here, if we dropped 3 different balls and each one had a different amount of bounce factor, if you will, that is the elastic potential energy. So for instance, if you drop, maybe this first one is a tennis ball, it has a lot of potential energy and it's elastic energy. Maybe the second one is just a marble. It's still going to bounce, but it's not going to bounce nearly high. And then the last one, maybe this is just like a clay ball. You drop it, it's going to hit the ground and it's going to stop. So that's what elastic energy is. Chemical potential energy is energy that is stored inside of a substance using chemical bonds. So for instance, this is an example of coal. When you burn coal, it's releasing that energy that was originally stored chemically. So it's still energy inside of here, and it's still potential because it's not actually moving or doing anything, but it is chemical potential energy. Another example would be the batteries inside of a flashlight. Those batteries are providing energy to the flashlight, and that energy is stored as potential energy. The last one that we're going to look at for potential energy is gravitational energy. Now, gravitational energy is energy based on an item's position. This is where we actually are going to start using an equation to calculate potential energy. So this is an equation you're going to want to remember. Potential energy is equal to mgh. That's mass times gravity times height. And the gravity is an acceleration. So we learned about acceleration in the last few lessons. We're now actually using the acceleration from gravity. For instance, on Earth, it's 9.8 meters per second squared. But it can be different in different places. And then the mass is just the mass in kilograms, and the height is the height in meters. So here's another example. That's a lot of gravitational energy that is just waiting to fall. And of course, if you're up on a high string, you might have some potential to fall, potential energy. So what we're going to do now is we're going to do some practice with potential energy and actually using that equation. So just a reminder, that equation is kinetic energy, or sorry, potential energy, PE equals mgh. And so what we're going to do is we're going to find the potential energy for each of these locations on this roller coaster. So we're going to look for A, B, C, and D. Now, if you're not told the gravity acceleration, just assume 9 times out of 10 that it's 9, I need to move my pen, 9.8 meters per second squared. Sorry about that. So we're going to try this out with our first location on this, which is at 10 meters. So we're told to consider the roller coaster on the right. How much potential energy does the coaster have at each point, A, B, C, and D, if it has a mass of 150 kilograms? So right off the bat, I'm going to circle my 150 kilograms because I know this is going to be something I'm going to need to plug in to my equation. So we'll start with our equation. Potential energy is equal to mass times gravity times height, which is going to be equal to our mass of 150 kilograms times gravity. If you remember, gravity on Earth is 9.8 meters per second squared, times the height. For this one, it is 10 meters high. And at this point now, all I have to do is multiply those three numbers. So I'm going to put into my calculator 150 times 9.8 times 10. And I end up with 14,700. Oh no, we don't know the units. The unit for energy is joule. Joule. We can shorten that for units and we just write J. So at that point, the potential energy is 14,700 joules. Or, if you remember a little bit of that kinetic, or the metric system, 14.7 kilojoules. I usually put a little line above my J's. So now we're going to look at the location B. So this was A. Now we're going to look at B. And again, we're doing the same equation. Potential energy is equal to mass times gravity times the height. Our mass has not changed. It's still 150 kilograms. Our gravity has not changed. It's still 9.8 meters per second squared. And our height is the only difference. We are now at a height of 5 meters. So before I even put that into my calculator, if the height is half what it was at A, could you guess what the energy should be if the mass and the gravitational acceleration are the same? If you guessed half, you are correct. 7,350 joules. Just to be safe, I'll put it into my calculator just to make myself feel like I know I'm doing what I'm doing. So 150 times 9.8 times 5 this time, 7,350 joules, or 7.35 kilojoules. Next up, we're going to look at point C. So on this location, you can actually see here, the roller coaster starts up high and moves its way, oh my goodness, and moves its way down. So the roller coaster starts here and falls. At this point, it has less gravitational potential energy because it is a lower point. So you can imagine if you were standing at the top of the roller coaster here and were to fall versus standing here and were to fall, the 5 meter height is going to be way less painful than the 10-meter height. Now the C is now where we've taken that roller coaster down and we're going back up. So we can assume now, because we're at a higher location, the potential energy should be higher than it was at point B. So again, we're going to plug this into our equation. Potential energy equals mass times gravity times height. Our mass and our gravity have stayed the same, 150 kilograms and 9.8 meters per second squared. The only thing that's changed is our height, which is now 7.5 meters. And if you can guess, we're going to be right in the middle of the two answers we've gotten so far. 150 times 9.8 times 7.5 gives us exactly 11,025 joules, or 11.025 kilojoules. Last but not least, we're looking at point D. So if the potential energy is at its highest at the highest height, what do you think the potential energy is going to be when it's down at the very bottom? Well, hopefully you've guessed that it's going to be much, much lower. And for that, we're going to plug in our equation, mgh. Our mass, again, still the same, 150 kilograms. Our gravity is still the same at 9.8 meters per second squared, but our height this time is 0 meters. And hopefully you know that anything times 0 is going to give you 0 joules, or 0 kilojoules. Hey, didn't have to do any conversion with that one. So this is potential energy. This is how you can calculate potential energy for this roller coaster. Let's try it again, but this time we're going to look at a rock. The rock is being dropped on the right, so it's going to fall, which makes sense. Imagine maybe somebody's got their hand and they're holding it. Yep, that's a hand. That's a claw. They're holding it and they let go. So before they let go, it has its most potential energy. The potential energy at this point, A, is going to be its highest. We can assume that the potential energy at C will be its lowest. So what we're going to do is we're going to calculate the potential energy for each point. Again, our potential energy equation, I keep putting PKE. Potential energy is equal to M times G times H. But this time, we are not given a mass or the gravitational effect. We're given newtons. Because there's another way you can calculate potential energy with something we've already talked about. Instead of mass and gravity, mass times acceleration, do you remember another equation that was equal to mass times acceleration? If you remember, force is equal to mass times acceleration. And the units for force are newtons. So we're told that this has a weight of newtons because weight and mass are not the same. Weight changes based on what location you're at. If you're on, say, Earth, you have a certain weight. Then you go to the moon. You don't weigh as much on the moon. The reason you don't weigh as much on the moon has nothing to do with the fact that you lost weight. What it has to do with is there's less gravity on the moon, so the force of your weight is less. Your mass stays the same. It's the acceleration that changes. But if we have the force, we can actually skip mass and gravity and just go straight to force times height. If we know the force, we can multiply it by the height to find the potential energy. So in this case, the force is going to be 5 newtons. At location A, our height is 14 meters. So we just have to take 5 times 14, putting that into our calculator, or doing it in our head if we can, and we end up with 70. Now we still do newtons. We haven't changed anything on our units here, so our units at the end here are going to be the same, and we're going to have 70 joules. Much less because this has a much smaller mass. This is probably more like a pebble. At location B now, we are at half of the height, so our potential energy should be half of what it was. But let's find out just in case. Force times height. Our force is still 5 newtons. Our height is now 7 meters. 5 times 7 is 35 joules. And then finally at point C, our force has not changed. The force is still going to be 5. The height is 0. And that is what makes our answer become 0 joules. So this is how you can calculate potential energy using mass, gravity, and height. Now we're going to look at kinetic energy. And kinetic energy is energy that is on an object due to its motion. The equation for kinetic energy is the kinetic energy is equal to 1/2 the mass times the velocity squared. So m is the mass in kilograms, v is the velocity in meters per second. So when we dropped this weight and cut it, the potential energy forces the weight to fall. The kinetic energy is the movement energy. Because remember, the total energy here, the total energy at all points does not change. What changes is that it is no longer potential energy, it turns into kinetic energy. So here's an example here where we're looking at a roller coaster, for instance. Now on this, we have 3 meters. We have a kinetic energy meter that tells us how much energy there is in kinetic. We have a potential energy meter that tells us how much of our energy is potential. And then our TME, which is our total mechanical energy. So you notice that as this roller coaster goes through, the TME stays the same at all points. It never changes. What changes is the potential energy turns into kinetic energy, and then as it goes back up and gets higher, some of that energy goes back to being potential. Again, some of the energy goes back up. As it goes up this hill, there's less kinetic energy, and that's why you slow down. So you can see that the speed down here changes because as you get more kinetic energy, you're going to have more speed. And it seems kind of intuitive. Hopefully you know this. As you drop something, it speeds up as it goes down. But just like when you take a, say, tennis ball, if you take a tennis ball and throw it against the ground, it's going to be going its fastest right when it hits the ground. And then it's going to bounce back up. And it'll slow back down and eventually come to a complete stop in the air because it's all potential energy and no kinetic energy. And then it falls back down and converts back to kinetic energy. Another example here is a skier going down a slalom. I don't know what you would call that, a hill. Now, in this case, we actually lose energy because we have energy converting. So in this area down here, we have unpacked snow, and that unpacked snow slows the racer down. That doesn't mean that the total energy is going away. What's happening actually is that energy is converting into work. That's what makes this total energy go down. The energy still has to go somewhere, and it's going into the snow. So in this case, the energy from the skier goes into the snow, leaving behind a snow trail, probably melting some of the snow as some of that energy turns into heat. So now what we're going to do is we're going to go back to that roller coaster we looked at, and we're going to look at the kinetic energy. Now, in the roller coaster, we're going to assume the roller coaster starts right up here, and it's not moving. So right before it falls, we want to know how much kinetic energy. So remember, the equation for kinetic energy this time is equal to 1/2 the mass. Learning how to use this pen again, times the velocity squared. So in this case, the kinetic energy is going to equal 1/2 of our mass, 150 kilograms, but it's not moving. And because it's not moving, the velocity is going to be equal to 0, which means how much potential energy, how much kinetic energy is there? Well, kinetic energy is going to be equal to 0 joules. But there's still energy in this system. What is that energy? Well, that energy is in potential energy. And so now we have to consider both of these, potential and kinetic. Remember, potential is mgh. We solved this earlier where we had our mass of 150 times 9.8 times 10. And if you remember from before, when we plugged those into our calculator, we got 14,700 joules. So our total energy is just the potential energy plus the kinetic energy for right now. And in this case, our total energy at point 1 is going to just be the 14,700 joules. That's just point A. At point B now, we have a different situation. The potential energy, if you remember, at point B was equal to 7,350 joules. But the total energy is still 14,700 because of the conservation of energy. So where did that energy go? Where must that energy be? And the answer is in the kinetic energy. Because at this point, at point B, the roller coaster is now moving. It's speeding up. It's gaining velocity. So it has kinetic energy. The kinetic energy would be 7,350. And I figured that out by taking the total energy minus the potential energy to get my kinetic energy. So now if we go to point C, it's going to start slowing down again. And at point C, our total energy is going to be the same. It's still 14,700. So we remember from before our potential energy, which was mgh, so 150 times 9.8 times 7.5. Our potential energy was 11,025 joules. So where's the rest of the energy coming from? It's coming from our kinetic energy. So if I take my total energy of 14,700 and subtract the potential energy of 11,025, I'm going to get a total kinetic energy of 3,675 joules. At point D, the last point for us, the total energy is still the same, 14,700 joules. The potential energy, if you remember, at point D, because there's no height, was 0 joules. So what must the kinetic energy be? Hopefully you can see it should be all of the energy. So at this point, all of the energy has transferred to point D. Now what can we do with that information? I'm going to erase my screen really quick. And we're just going to focus on point D. Because what I want to know is how fast is the roller coaster going? What's the velocity at that point? So if I know that kinetic energy is equal to 1/2 the mass times the velocity squared, and I also know that the kinetic energy at that point is 14,700 joules, I can actually find out how fast the roller coaster is moving. By setting this equation up, the mass is 150 kilograms, and our V is our unknown. We need to solve for V. So the first thing I'm going to do is I'm going to get rid of this 2 by multiplying by 2. That'll cancel out here and cancel out here, and we're going to multiply this side by 2. We also want to get rid of the mass here, the 150 kilograms. So I'm going to divide this side by 150 kilograms to get rid of the 150, and I'm going to do the same thing to the other side. So at this point, I'm just going to plug into my calculator the 2 times 14,700 divided by 150, and what I'm going to get is 196. And that is equal to our velocity squared. Does anybody remember how you can solve for a square? Well, what number squared equals 196? So all we need to do here is find the square root, because by doing it to this side, I get v by itself, and I get the square root of 196 to find out what v actually equals. So I'm going to put that into my calculator as well and take the square root of 196, and I get 14 as my answer. And it's 14 meters per second. So just by finding the potential energy at point A, when we found the potential energy here to be equal to mass times gravity times height, I am now able to find out how fast it's moving at the end of the roller coaster. Now, we are making some assumptions. We're assuming no air friction or air resistance. We're assuming that there's no friction. And by making these two assumptions, we can determine the answer. Now, if we were to put this on a real roller coaster, it's going to be slightly smaller because there is air resistance and friction. But realistically, the difference is so small that we can do it this way and not have to worry too much about it. So we just did point D. We found out how fast it was going at point D. Remember, it was 14 meters per second. What I want to do now is find out how fast is it going at point B. So before we even do this problem, I want you to think about this. If it's going 14 at the end, do you think it's going to be going faster or slower when it's up higher? All right, so we're going to start by looking at our total amount of energy. Remember, total energy is equal to potential energy plus kinetic energy. We know in this system, the total energy is always 14,700 joules. We also, in previous problems, determined the potential energy at point B to be 7,350 joules, which made the kinetic energy 7,350 joules. So just by doing that, I now know with my kinetic energy equals mass times, 1/2 mass times velocity squared, I now have the kinetic energy, I have the mass, remember the mass is equal to 150 kilograms, and we can solve for V. So let's plug in our numbers. Kinetic energy is going to be 7,350. That's going to equal 1/2 times the mass of 150 times our V squared. Now I'm going to skip here. We're just going to get rid of the 2 here by multiplying this side by 2. We're going to divide both sides by 150 so that we can get our answer on one side. So I'm going to take 2 times 7,350 divided by 150, and now I get 98. And 98 is equal to our V squared. Remember, to solve for a square, we're going to take the square root of both sides. The square root of V squared is V. And the square root of 98, if I plug it into my beautiful calculator, is going to be 9.8994. I'm going to call that 9.9 meters per second. So at the beginning, I asked you to think, do you think it was going to be faster or slower at point B? So the velocity here was 14 meters per second. The velocity at point B then was 9.9 meters per second. So it's going faster at the end than it goes up here. And the reason for that is because half of the energy of the system is actually kinetic or potential energy. So there's not as much energy to help the roller coaster move. So at this point, you're going to complete a practice assignment that you'll find on Teams. The practice assignment is going to go through some of these types of problems where you're going to be solving for potential and kinetic energy as well as velocity. But remember, you can solve for any of these things if you have everything else. So if I had given you the velocity and the energy, you could have solved for the mass. So be prepared to solve for any of these unknown variables. Thank you for watching. Make sure you like and subscribe, and of course, hit that like button. Have a great day. I'll see you guys in class.